Hi guys, this is the first presentation on chapter 15 on metabolism basics. And so this chapter we're going to talk about common trends and big ideas that you really need to have moving into talking about metabolism. All right, so essentially, metabolism is a bunch of events, a bunch of chemical reactions that can be broken down into two classifications. Catabolism, which is breaking down our molecules to obtain energy and get reducing power. And then anabolism is the idea of making bigger macromolecules from basic building blocks. So catabolism, you can think of our hydrolysis reactions that we talked about in chapter 14. Those would all be examples of catabolic processes. And our condensation reactions of making our macromolecules would be examples of anabolic processes. All right, so this is a fantastic subway looking map of all of our metabolic processes that occur. We will not be going over all of these processes, but we will be focusing on carbohydrate metabolism, lipid metabolism, a little bit on nucleotide metabolism, and amino acid metabolism, a little bit. And then we'll talk about energy metabolism as well. All right, so in discussing catabolic versus anabolic, note that when we're doing catabolic processes, larger things becoming smaller things, we also get energy. So this would be referred to as an exergonic process, so a negative delta G, because our energy is being created. Okay, anabolic processes, we take smaller molecules, we need energy to put these things together to create larger molecules. Note, this is a big generalization. Okay, so in general, this is what happens. Some catabolic processes require energy at the individual reaction level, and some anabolic processes get energy out, but this is the overall trend and the big idea. All right, so our metabolic processes are super complex, okay? However, we tend to see overall general trends across all of them. So hopefully you've picked up on the idea that we keep seeing the same types of reactions occurring over and over and over again. And so that's how nature has simplified the super complex process of reaction. And we have kind of switches to turn processes on and off as needed when we are needing specific metabolites or processes to run. And this is turned on and off using allosteric regulation. So keep in mind, this is where we add something or take something away, typically a phosphate, from our enzyme to turn our enzyme on or off. Okay. So this whole idea is brought about by energy. Okay, so we do all of this to get the energy from the food we eat typically. Okay, so we need to have a little bit of a review about energy. We've talked a lot about it up to this point, but energy, keep in mind that the rule from Gen Chem still applies, that energy is neither created nor destroyed. Okay, so in biochem, our energy is just converted from one form to another. So phototrophs, they take energy from sunlight and convert it to energy biomolecules that serve as fuels. So you can think of our plants taking our sunlight and converting it to our starches that are amylose and amylopectin that we can then eat and then utilize as fuel. Okay, so note that that energy is just a flow and we still maintain the same energy. And chemotrophs obtain chemical energy through oxidation. So let's think about this. The plants take our energy from the sunlight, convert it to our amylose and amylopectin that can be used for us as chemical energy through oxidation of those biomolecules. All right, so with that, we have to consider how some of our reactions and processes that are unfavorable actually occur. So we talked about this a little bit when we talked about antiport transport. Okay, so what we did there was we took a process that would be unfavorable, going from a low concentration to a high concentration, that would be unfavorable, right? And we utilized ATP hydrolysis to provide the energy for that process to occur, right? And we also have the opportunity to couple that process with a reaction or transport going from low to high, or high to low, right? So that's another opportunity where we have a coupled thermodynamically favorable reaction with a thermodynamically unfavorable reaction. So what do I mean by thermodynamically unfavorable? A thermodynamically unfavorable would be our unspontaneous, our non-spontaneous process, or positive delta G for the reaction. So this is where Hess's law comes into play, where we can add up the energies associated with each process or each reaction and get an overall delta G for that process. So if one reaction requires a certain amount of energy, we can couple that with a reaction that releases more energy than what was required to get an overall spontaneous reaction. Note, a lot of you missed this on the exam, that we are using the chemistry definition of spontaneous. And so all that means is that energy is not required for the reaction to occur, right? This says nothing about how fast or slow the reaction will occur. All right, so what do we typically use as our energy source? Well, as many of you already know, ATP is our energy currency. Okay, air quotes there for currency. And so ATP has phosphoanhydride bonds associated with it. Okay, adenine, remember ATP is just a ribonucleic acid. And so we have other options for this. We have UTP, GTP, and CTP, right? Uracil, guanine, and cytosine, in addition to our adenine. Okay. Typically, we see the ATP, but we will see instances in some metabolic pathways where we utilize the other ribonucleotides. All right, so what type of energy do we get out of this? Remember, we aren't getting energy just from breaking off a phosphate. Remember my hands together, right? It takes energy to break this bond. No matter what bond it is, even a phosphoanhydride bond, it takes energy to break this bond, okay? But when we consider the overall summation of the energy that it takes to break these bonds versus the energy that was released when we made these bonds, we get an overall negative value, okay? And so from that, when we break one phosphate, we get negative 7.3 kilocalories per mole. Do you need to memorize this? No, but it should be something that you use a lot to where you get used to it, okay? If we break off this phosphate versus this phosphate, we get AMP, adenine monophosphate, meaning we only have one phosphate. And we would have broken off these two. This would be referred to as pyrophosphate, okay? Breaking off this, are hydrolyzing, the overall reaction of hydrolyzing this phosphoanhydride bond, we get negative 10.9 kilocalories per mole. So why is there a difference in this bond energy? Well, it depends upon where we have this magnesium ion stabilizing this phosphate. Okay, so if the magnesium ion is stabilizing here, and we are going to hydrolyze off this end phosphate group, it doesn't provide as much energy, okay? Versus here, this leaving group is super stabilized, and so we get a lot of energy when we release this pyrophosphate versus this single phosphate. All right, so overall, remember delta G is not just the heat of reaction, so our enthalpy, but it also takes into account our entropy. And so that's, remember, the amount of disorder. So let's think about all of the ways in which we get why we get this high negative delta G for ATP. The first of which is that the energy of our phosphoanhydrides, the first of which is electrostatic repulsion. So when we look at ATP, if we look at ATP, there's a lot of negative charges all here. And so when we take off a negative charge from there, we get a lower energy product than what we started with. And so because of that, we get a negative delta G. There's a negative difference. The products are lower in energy because of one of the reasons is this electrostatic repulsion of the negative charges of your oxygens. We also have resonance stabilization. So if we look at phosphate here, we have lots of different resonance structures, which we'll see on the other slide, compared to the possible resonance structures in ATP. And as you know from organic, the more resonance structures we have, the more stable, the lower in energy your molecule. And so if we look at all of the various resonance structures for a phosphate group, we have 4 different resonance structures. And so we have lots of places for our electrons to be delocalized. And then finally, we have stabilization due to hydration. So it's much easier to have these hydrated, our phosphate groups, be hydrated versus the overall ATP, okay? And because of these 3 reasons, that's why our products are lower in energy than our reactants, okay? And so we can look at that here. Here, our ATP is plus water is super high in energy compared to our products. And because of this, we get a large negative delta G. So this large excess of energy that is released, we can couple with our reaction that requires energy. So adding a phosphate group to glucose requires a lot of energy. So this is the typical reaction we show for coupling. It's also the first step in glycolysis. And when we add these 2 delta G's together, we get an overall negative delta G. And so we can see how we did that in this step here. Remember, if the delta G is positive, that would mean that it is a reactant. It's required for the reaction to occur. If the delta G is negative, that would mean that our energy is released and therefore a product. So if we do Hess's law and cancel out all of the things that are on both sides of the reaction, so water and phosphate, we get our overall reaction for step 1 of glycolysis, and we also get an overall negative delta G, which would be 4 kilocalories per mole when we subtract these 2, and it's a product, so that would mean that it's negative. All right, so ATP isn't the only compound that is energetically favorable. This we also have other molecules, other metabolites that are involved. I'll stop here and I'll start here on the next